Alright, so I have our integral process all set up and running. You can see the flow in matches the flow out, or pretty close at least, and our levels remaining constant here. What I'm going to do now is I'm going to introduce frequency here. I'm going to take our valve and start opening and closing it and see how it responds, because this is kind of the basis behind our Bode diagrams that we're doing, and I wanted to kind of prove that. This is an integral process. We have the pump off the bottom there. The outflow should remain pretty constant. What I'm going to do is with our signal generator here, I'm going to generate a wave with a period of 60 seconds, which should take up about our whole graph here. So it's set to 60 seconds. The bias is set around the black line here, so it's going to oscillate around this black line at 62%, which is our output to our valve. And our amplitude is going to be a total of 20%. So what I'm going to do is I'm going to go ahead, you can see our frequency. I've got this calculating what our frequency would be based on that period. It's 0.1 radians per second. We'll go ahead and enable this here, and we should see our controller output. It should start to oscillate, and you can see our levels wanting to follow it there. So it's starting to oscillate, and it's going to have a period of 60 seconds, so we'll have to wait a little bit for this to happen. If we look over here at our process there, our level's dropping right now, and it's just starting to come back up again on the trainer. So if we have a look over here, you can see it all happening. So once it hits about, once we hit about 62% here again, we should see our process turn around and go the other way here, the blue, which is the process. And there you can see it's turning there again, and it's going down. And so with a integrating process, we should see a phase shift of about 90 degrees from the process to the signal that's going in, which is our signal from our going into our valve. So if this was the top here, 90 would be down somewhere around here, and that's right about where the middle of this peak is. So we're about 90 degrees away from each other with this. So the other thing that we want to, so we've confirmed that we're 90 degrees. The other thing that we want to figure out at this frequency is what our gain is. And our gain is going to be, this is our input signal here. So this total change, which we said was, should be about a total of 20 on either side. So our total, I guess if we, yeah, that might be the easiest way for us to do it, is go peak to peak, which would be a total of 40. Because our amplitude's 20, so the total difference here would be 40. And so if we divide that into the total difference here, then that should give us our gain right now at this particular frequency. So let's have a look here. We're going to drop down, and we'll have a look at this value here. We'll record it. It looks like right around, it was around 64%, I would say, is where it turned around here. Or sorry, we're looking at the wrong thing. That's the controller output. We want to look at this guy. So let's get it at the high end here. So it's going to probably change right away. 39, 40. So it turned around at about 41.5. So 41.5, and we're going to watch it come down to the lower end here. And when it starts to go up again, we'll record that. So 41.5 and $20.2, 41.5 and 20.2. So the difference there, that difference divided by 40 would give us our gain. So what we'll do now is we'll go and we'll calculate a different value here for a higher frequency and see what that does to our gain here, the change in input versus the change in output of our wave. All right, so I went and adjusted our period over here. I went from 60 to 30, and you can see our radian value, rads per second value increased. And what's still the same here is our amplitude. It's still at a total of 40 peak to peak. But down here now you can see that our amplitude has shrunk. We increased our frequency and the amplitude went down. So that's probably going to indicate that our gain value is going to become less. So let's figure out what our gain value is, get the values to determine our gain value. These are still the same, but now our frequency is different. So we've got a new radian per second value here. And down here, let's just record our values here. Our process here is dropping down, and 16.8 is the bottom end. And we're going to come up here and watch for it to turn around and go back down. 16.8 and 26.4 are the two values that we got. So we're going to take those values, take the difference between those two. That'll tell us our peak to peak here, and we can divide that by 40 again to get our gain at that new frequency. So we'll do one more frequency here, and I think that'll give us a good idea and kind of prove that the integral process does what we expected. And you can see we should still be pretty well at a 90-degree phase shift here. We're about 90 degrees off on the wave here. Coming up the peak here is right around where it intersects here. So it's moved by about 90 degrees on our wave. All right, so I've lowered our frequency here, or sorry, our period again to 15, and it increased our frequency to 0.42 radians. And you can see amplitude still the same going out to our valve here, but now our level, the amplitude, the peak to peak amplitude is decreased even more. And we were recording about let's watch this value here, 38.7 down to 34.6. 38.7 to 34.6. So we take the difference of those two again to get our peak to peak value and divide it by our peak to peak value of our sine wave that we're inputting into our process. And that then will give us our gain. And the frequency, or sorry, the phase shift is still pretty close, I would say, to 90 degrees here for our process. So pretty good, pretty well at integrating process. Like I mentioned before, the pump, we're not using a true positive displacement pump on our system, but we are drawing the liquid off the vessel with this pump down over here, and gives us a pretty close to an exact integrating process, but could be slightly off. So there we have all of our readings now. We should be able to take our data that we've gotten here and compare it to what we predicted for this process.
All right, so I have a first order process right now. You can see our pump's gone here. First order process, and I've got it, we're inputting, the valve is oscillating at a frequency of 0.1 radians per second, or an amplitude of 20 seconds. Sorry, period of 60 seconds and an amplitude of 20. And so what we want to check now here is we want to check to see what the gain is here of our first order process. So to do that, what we'll do is we'll just quickly watch our process variable here. I guess we could also take this value right here. It's the same thing as looking over here. When it hits the bottom here, we want to write that number down. I'm going to take the difference between the peak to peak. So it looks like it should be turning around here soon. So it looks like 20.86 for our lower value. And then we're going to climb back up here. We need to record the top value, so we get a peak to peak value for this. And there we hit it. We were about 30, 33. Okay, so now we're going to go and change and source a new frequency for this. And see what that does to our first order process. Alright, so now I have adjusted our frequency here again. Period is 30 seconds to complete the wave. And we're going to grab our peak-to-peak value for our process. So it looks like we're coming down here right now. So we're at 21.74. Now we're climbing up again. And looks like about 28.1 for the 30-second period. All right, now I've just increased our frequency even further, decreased our period by down to 15, and we're just going to get our peak-to-peak values here. So it looks like on the high end, 28.3. Coming down to the low end here, 25.54 I saw.